We have this example with a pre-stress, let's say concrete beam. But anyway, the pre-stressing force is 100 kips compression on either side of the beam, and we said the beam was 2 foot by 2 foot, and this pre-stressing force is located 6 inches below the centroidal axis. And we want to find the maximum combined stress on the top and the bottom of the beam. All right? So, like I said in the previous example, the place that I like to start on here is just, you know you've got to have P, A, M, C, and I, and you may as well just figure those out first, get them sort of there on the page, and then you can figure out how you're going to deal with them. But the force that's causing the axial stress is a compression force, and so that's 100 kips, and again, like we did the last time, we'll call it minus. All right? The area is what? What's the area? 2 by 2, right? That's the area that the force is acting over. So that's 4 square feet. What's the moment? We talked about this earlier when we were introducing the concept of pre-stressing. There's a moment because this force is offset, or the force is eccentric from the centroidal axis. What would the moment be? Well, you got a 100 kip force, but a moment is a force times a distance, right? So how far is it offset? 6 inches, or 6 inches could be called a half a foot. So your moment, 100 kips times 0.5 feet, hey, that comes out to 50 foot kips. Right? Your C distance. What's your C distance here? A half? No. C distance is, if we're looking for maximums, the distance from that neutral axis, in this case the centroidal axis, to where? To the edge, to the outside edge, top or bottom. So how much is that distance? 1 foot. Moment of inertia, again, this is a square, but we treat it just like the same formula we'd use with a rectangle. 1/12 BH cubed. In this case, B and H are the same. So that comes out to be 1.33 feet to the fourth. Okay? All right, so again, I take P over A, I calculate that little formula real quick. That's going to give me minus 100 divided by 4. Negative 25 KSF, kips per square foot. Okay? The bending stress portion of it, MC over I just want to make sure that I'm using the right units, but it's 50 foot kips times C is 1 foot divided by 1.33 feet to the fourth. So I got 50 times 1 divided by 1.33, and that comes up to be what? $37.5. Again, the units here, because I'm all mashed up, would be kips per square foot. Now, the question you have to ask yourself is this. You know, this moment sort of flexes the beam up in the air like this. So where does it put tension and where does it put compression due to the bending? Tension's on what side? Is it on the top or is it on the bottom? Well, tension's going to be on the top. If it's flexing it up like this, you know, that side's going to be in tension. So again, if it's, you know, flexing it up in the air like that, you know, that top side's going to be in tension. Okay? So what I would do then is I just construct, you know, you got all your stuff here. Top is tension, bottom compression. I just construct a little table, you know, sort of like I did the last time, you know, and just basically have all the components in it, you know. P over A, MC over I, and stress combined. Then you have top, for top of the beam, bottom, for bottom of the beam. What's P over A for both cases? Minus 25 kips per square foot. Top of the beam, the MC over I, bending stress is what? 37.5, is it positive or negative? Positive, because it was tension in the top. It's going to be negative in the bottom. Then I just add it up. Minus 25 plus 37.5 for the top of the beam leaves me with plus 12.5 KSF in the top. For the bottom, now you got minus adding to a minus, so that gives me minus 62.5 KSF in the bottom of the beam.